It seems like just yesterday we were all blown away by AI making still images, and now it's all video, video, video. It's moving so fast. Look at all the hype around models like Sora, and it's definitely for a good reason. I mean, what these things are doing is amazing. Creating videos that would have sounded like straight up sci-fi just a little while.
It really is remarkable how quickly this field is advancing. And actually, speaking of pushing the boundaries, there's this new model called Wan.
One, okay.
Yeah, it's from Alibaba,
Alibaba.
and they've just released this whole suite of open video foundation models. They have a 1.3 billion parameter version, and then they've got this other one that's a whopping 14 billion parameters. Clearly, they're aiming high.
They're not messing around, that's for sure. And for this deep dive, you've shared some really interesting stuff about Juan with me. And we're going beyond just looking at the cool videos it makes, right?
Right.
We're going deeper to get into the science behind it, the more academic side of things. What are the really innovative aspects? What are the things that let Juan achieve this level of performance? What makes it different from an engineering perspective?
Exactly. So they talk about Wan as having four key features: leading performance, being very comprehensive, consumer grade efficiency, and openness.
Okay.
And while all of those are important, what we want to focus on here is those innovations. We want to really understand how they made those design choices, those new training methodologies, and how those contribute to Wan's capabilities.
Okay, so let's start with the first of these big technical innovations, the spatiotemporal variational autoencoder, or VAE. We know that VAEs are really important for generative models when dealing with complex data, especially when you have something as rich as video.
Right. Think of the VAE as a super efficient organizer for data. It takes this huge amount of data in a video file, high dimensional data, and figures out how to represent all the essential information in a much smaller, organized way. This compact representation makes it a lot easier and faster to actually train the video generation model like the diffusion model in one.
Okay, but video is so much more than just a bunch of images strung together, right? There's this whole aspect of time, the way things change and move in the video. What are the challenges from a research perspective in designing a VAE that can actually capture this spatiotemporal nature of video?
That's a great question, and it highlights some of the core theoretical hurdles. First, the VAE needs to figure out all these complicated relationships, not just between things in a single frame, but also how things change across frames over time. These are called spatiotemporal dependencies.
Okay.
Then there's the fact that video files are just massive. It's so much data, all these high-res frames, and that makes compressing the data a huge challenge. And finally, and this is really key from a research point of view, we have to make sure the model understands that the past influences the future, not the other way around. We call this temporal causality.
Okay, and this is where one VAE comes in with its new approach, right?
Right. So one VAE is what they call a 3D causal VAE architecture. They've combined these smart strategies to get much better spatiotemporal compression, which means they can use less memory, and that's a big deal in video processing. And that causal part of the name, that's there because the design specifically enforces that time moves forward, not backward. They even suggest that this design makes it a perfect fit for diffusion models, particularly one called DAT, which we'll talk about later.
Interesting. The paper also mentions some interesting changes they made even to the basic building blocks of the network. They replaced something called group norm with RMS norm layers. What's the reasoning behind that in the context of video VAEs?
That change is all about preserving temporal causality. Group norm, which works well in a lot of computer vision tasks, can sometimes accidentally let information leak between different points in time within a video. And RMS norm, on the other hand, normalizes the features in a way that keeps the flow of information going in the right direction from past to future. This choice also supports the way their feature cache mechanism works.
Yeah, the feature cache. It seems like a really interesting idea. And the paper even has this diagram, figure 6, to illustrate it. Can you explain what it is and why it's so important for video modeling?
So imagine you have a super long video. You can't process it all at once. You need to break it up into smaller pieces, right?
Right.
But the problem is that when you do that, you can lose the connections between those pieces. It's like starting a new story every time you move to a new chunk. The feature cache is designed to fix that. It remembers information from the pieces that came before. Figure 6 shows how it works.
Okay.
Those cached features are used when processing the current piece of the video, both for the normal operations and when the model is trying to understand the changes happening over time. This way, the model doesn't have to relearn everything every time it moves to a new chunk. It can just use what it remembers from the cache. This saves a ton of memory because the model doesn't need to keep the whole video in mind.
Interesting.
But even more importantly, it theoretically means you could process or even generate videos that are basically infinitely long and still keep everything making sense over time.
So this WAN VAE, with all its clever design choices, does it actually work better in practice?
Yeah, so they actually did some experiments to compare it to other VAEs. You can see those results in Figure 7. They looked at a metric called PSNR, which basically tells you how good the reconstruction is. And they also measured how fast the model can process video frames per second.
Okay.
To make the comparison fair, they only compared it to other models that had similar levels of compression and similar size latent spaces. The results show that WAN VAE is at least as good and sometimes even better than other state-of-the-art models, both in terms of how well it reconstructs videos and how fast it runs.
And we get to see some actual visuals too, right? Figure
Yes.
8.
Figure 8, qualitative results are important, but sometimes you need to see it to believe it.
Yeah.
So they included some visual examples of how well 1VE reconstructs videos. They used all sorts of challenging videos, like ones with complex textures, human faces, text, and lots of motion.
Okay.
And you can really see in those examples that 1VE does a good job of keeping all the details and avoiding things like blurriness or weird distortions. There's one example where it reconstructs text from a video perfectly, and another where it keeps a moving object sharp even though the model has never seen that kind of motion before.
That's really impressive.
So to sum it up, this new VAE architecture with its POSL design, RNS NORN usage, and feature cache mechanism is a big step forward in how we efficiently and consistently encode all the complex information in videos.
Okay, so we've talked about encoding video efficiently, but how about actually creating those videos? Let's move on to the core of the generation process, the video diffusion transformer and the training methods they used. Figure 9 gives us a nice overview of the whole WAN architecture. What are the key parts here from a research perspective?
Yeah, so Figure 9 shows us that the WAN fusion process has three main modules.
Okay.
The first one is the WAN encoder, which we already talked about, and that's what takes the video and creates that compact representation. Then you have a bunch of what they call DIT blocks stacked together.
DT blocks.
Yeah, and those are the diffusion transformer blocks that actually predict the noise and generate the video. And finally, there's a T5 text encoder.
T5. Okay.
That one's really important for processing the text prompts that tell the model what kind of video to make.
So it's understanding the instructions.
Yeah, basically. So the encoded video from WAN VAE goes into those DT blocks, and they're also getting information from the text embedding from T5 and about where they are in the diffusion process, which is like a time step.
Okay, and then Figure 10 goes deeper into the architecture of each individual DIT block. What's interesting about its design from a technical point of view?
Figure 10 shows that each DT block starts by taking the video's latent representation and breaking it down into these smaller chunks called feature patches. These patches then go through the transformer layers, which are specially designed to understand both the spatial and temporal relationships within the video. They also incorporate information from the text and those time step embeddings. One of the cool things they did is to use cross-attention mechanisms to incorporate the text instructions.
Okay.
This allows the model to focus on the right parts of the video based on what the text is saying, even if the instructions are long and complicated.
So it's like it's paying attention to the important parts of the instructions.
Exactly. And they have this new kind of MLP, a multi-layer perceptron, that's designed to process those time embeddings and figure out the modulation parameters that are used inside the DID blocks. And their research shows that this new design actually reduces the number of parameters in the model while also making it work better.
Wow, less is more sometimes.
Sometimes. So to train a model this big, you need some pretty advanced strategies, and they've come up with some really interesting pre-training and training methods to make it possible. One thing they do is use this thing called the flow matching framework, which is a really solid way of training generative models that work in continuous time.
Okay.
This framework lets them use the same denoising process for both images and videos. So they start by pre-training on low-resolution images using this flow matching approach.
Okay.
Then they move on to this multi-stage joint training process that includes both images and videos. And with each stage, they increase the resolution of the images and videos, and they make the videos longer.
Okay.
This staged approach is really important because if they tried to train everything on high-resolution, long videos right from the start, it would take forever and use up way too much memory.
That makes sense. They also mentioned something called rectified flows, or RFs. What are those and how do they work in this training process?
Okay, so rectified flows, they basically provide a map in the latent space, kind of like a roadmap to guide the diffusion process. So you start with a bunch of noise and you want to end up with a nice clean video latent, right?
Right.
The RF defines a path between those 2 points. If you look at equations 1 and 2 in the paper, they show how this works mathematically.
Okay.
The intermediate latence xt at any given time t is just a simple combination of the initial noise x0 and the clean latent x1.
Okay.
Then you have the ground truth velocity, VET, which is the direction the model needs to learn to go from the noisy latent to the clean one. And then equation 3 shows the loss function, which is basically how the model learns. The goal is to minimize the difference between the velocity the model predicts and the actual ground truth velocity.
Okay, so the model is essentially trying to learn how to steer the noise towards the desired video.
Exactly. And this formulation makes training a lot easier and more stable than directly predicting the noise itself. And it's interesting that they start with images. It's almost like they're teaching the model to walk before it can run, mastering the spatial domain before tackling the more complex temporal domain.
Yeah, that makes sense.
And they actually have data to back that up. In section 4.3.1, they talk about their workload analysis. They found that the self-attention mechanism in the DIT model uses the most computing power, and that problem gets a lot worse as you make the video sequences longer. The math behind it shows that the computations needed for attention grow much faster than the memory usage as the sequence length increases. So if they started with long videos, it would just be too much for the computers to handle.
So how do they actually train this model? It's so big and the data is so huge. They must have to use some pretty serious computing power. What kind of distributed training strategy did they use?
Yeah, they had to get creative. In section 4.3.2, they talk about how they parallelize the training process across multiple GPUs.
Okay.
They use a combination of different techniques. For the VAE and the T5 text encoder, which aren't as demanding computationally, they mostly use data parallelism.
Data parallelism.
That basically means that they copy the whole model to each GPU, and each GPU gets a different batch of data to work on.
Okay.
But for the DIT module, which is much bigger and more complex, they combine data parallelism with something called fully sharded data parallelism. That one, FSDP, is all about saving memory. It takes the model's parameters, gradients, and all the optimizer states and spreads them across all the GPUs so no single GPU gets overloaded.
Like dividing and conquering.
Exactly. And then to deal with those super long video sequences, they came up with this cool thing called 2D context parallelism.
2D context parallelism. Okay, tell me more about that one.
So that's one of their key innovations, especially for handling these long-range dependencies in time. Imagine you have a bunch of computers working together to process a long video. Usually they need to constantly talk to each other to share information. That communication can really slow things down.
Right, so reducing that communication is a key.
Exactly. And that's what 2D context parallelism is all about. It combines two techniques, Ulysses and ring attention, and basically it partitions the data along the sequence length dimension, the S dimension, on top of the usual data parallelism.
Okay.
And the result is that they were able to cut down the communication overhead by a huge amount. In their tests, with 256,000 sequence lengths and 16 GPUs, they went from over 10% overhead down to less than 1%. Figure 11 shows you a diagram of how this distributed training scheme works.
So they're basically fine-tuning how the different parts of the model talk to each other.
Yes, and they've even built in a mechanism that switches between different strategies depending on what's happening in the training process to avoid unnecessary calculations when the VAE and text encoder are feeding data into the DIT module. It's all about squeezing out as much efficiency as possible.
And with a model this size and these long video sequences, memory management must be a huge issue. What techniques did they use to deal with that? They talk about it in section 4.3.3, right?
Right. So they realized that the problem is that the computational cost grows much faster than the memory usage as you make the video sequences longer. So their main focus is on something called activation offloading. Basically, they moved the intermediate results of the calculations from the GPU memory, which is fast but limited, to the CPU memory, which is slower but much larger. And they try to do this offloading while the GPU is busy with other calculations to minimize the slowdown. They found that for certain layers in the model, the ones that use a lot of memory but don't require that much computation, offloading is more efficient than another technique called gradient checkpointing.
Okay.
But if they run out of CTU memory, then they combine offloading with gradient checkpointing. It's a really clever balancing act to manage all that data.
So these distributed training and memory optimization techniques are really fundamental to making this kind of research even possible, right? It's not just about fancy algorithms. It's about pushing the limits of what our hardware can handle.
Exactly. Without these innovations, developing models like Wang would be much, much harder, if not impossible, given the computational resources we have today.
Okay, so we've covered how they encode the video and how they train this massive model. But what about actually generating videos once the model is trained? That's the inference process. And Section 4.4 talks about how they optimize that.
Right. So the main goal during inference is to make the video generation as fast as possible. You want to minimize the time it takes to go from a prompt to a finished video.
Of course.
Unlike training, which has a fixed number of steps, inference in diffusion models usually involves doing a bunch of sampling steps, often around 50 or so. So anything you can do to make each step faster or reduce the number of steps can significantly speed up the whole process.
And they talk about using parallelization again for inference, right? Is it similar to what they did during training?
Yeah, they still use context parallelism with ring attention and Ulysses to speed things up when they're using multiple GPUs. That's in figure 12. And for the 14 billion parameter model, which is a real memory hog even during inference, they use FSDP again to split the model across multiple GPUs.
Okay.
Figure 12 also shows how the inference time decreases almost perfectly as you add more GPUs, which proves that their parallelization strategy is working well.
Yeah, that's really important if you want to make this technology usable in the real world.
Absolutely. They also came up with this really clever technique called diffusion cache to optimize the sampling process.
Diffusion cache, how does that work?
So the basic idea is that they realize there's a lot of redundancy in the sampling process. The results you get from one sampling step are often very similar to the results from the next step, especially when it comes to the attention mechanism.
Okay.
And then later in the sampling process, the outputs for the conditional and unconditional parts of the process, which is part of how they use classifier-free guidance, also become very similar. So they figured, why calculate the same things over and over again?
Yeah, why not just save the results and reuse them?
Exactly. So they implemented this caching strategy. They only do the full attention calculation every few steps and reuse the cached results for the steps in between. And they do the same thing for the CFG calculations, reusing the results from the unconditional part for the conditional generations.
That's pretty smart. And how much of a speed up did they get?
Oh, it was significant. They got a 1.62x improvement in performance on the 14 billion parameter model just by using this caching technique.
That's huge. And they also experimented with quantization, right? Using lower precision numbers to speed up the calculations.
Right. In section 4.4.3, they talk about how they explored using lower numerical precision during inference.
Okay.
They found that using FP8, which is 8-bit floating point, for the matrix multiplications within the DIT blocks gave them a huge speed up without sacrificing much in terms of video quality. They got a 2x speed up over BF16, which is 16-bit floating point, and a 1.13x speed up specifically within the DIT module.
And they also did some work on optimizing flash attention, which is known for being very efficient for transformer models.
Yes. Just switching flash attention to FP8 directly didn't work very well for their video generation tasks, so they created a custom 8-bit flash attention implementation that uses a mix of precisions. They use int8, 8-bit integer for one part of the calculation, and FP8 for another part, and then they use FP32 for the final accumulation step to ensure numerical stability. And they carefully chose the block size parameter to optimize how the hardware uses its registers. This custom implementation achieved really high utilization of the NVIDIA H20 GPUs and gave them another 1.27x speedup in inference.
Wow, so they really went all in on optimizing the inference process. It's amazing how much faster they were able to make it without sacrificing quality.
Yeah, all these optimizations, the parallelization, the caching, the quantization, they're all essential for making this powerful model actually usable in real-world scenarios. Without them, the computational costs and the time it would take to generate videos would just be too much.
Okay, so we've talked about the technical nuts and bolts of the model, but there's another aspect that's equally important, and that's making sure the generated video actually matches what the user intended when they wrote the prompt. Section 4.5 delves into their prompt alignment strategy. Can you tell us more about that?
Absolutely. You're right. There can be a disconnect between the concise prompts that users typically provide and the more descriptive captions that these large video models are trained on.
Right.
Their prompt alignment strategy aims to bridge that gap and make sure the model understands what the user really wants. They have a two-pronged approach. First, they train the model on a variety of captions for each video. These captions differ in length, level of detail, and style, so the model learns to associate different textual descriptions with the same visual content.
Okay, so it's like teaching the model to speak different dialects of the same language.
Exactly. And then the second part of the strategy involves actually rewriting the user's prompts to make them more aligned with what the model has been trained on.
So they're using an LLM for that, right?
Yes, they use a powerful LLM QN 2.5 Plus to rewrite those prompts, basically a set of guidelines they developed by studying high-quality video captions.
Okay, what are those guidelines?
Well, they focus on adding more specific details to the prompt without changing the main idea. They also try to incorporate descriptions of natural, plausible movements that make sense for the subject matter. And finally, they structure the rewritten prompt in a way that's similar to the captions they use for training, usually going from a general style instruction to a more abstract description, and then finally to a very detailed description of the scene and the actions.
That's really interesting. So it's almost like they're translating the user's prompt into a language that the model understands better.
Exactly. And Table 1 in the paper provides some great examples of how they transform user prompts using this rewriting process.
Okay, I'll have to check that out. So by making the user's input more like the data the model was trained on, they're essentially giving it clearer and more familiar instructions, which should lead to more accurate and relevant videos.
Precisely. This prompt rewriting is a key part of making sure the generated videos actually reflect what the user had in mind.
Okay, so now let's talk about how they actually evaluate the performance of Wan. They've developed this new benchmark called OneBench, which is described in section 4.6. What was the motivation behind creating this new evaluation framework?
Yeah, they realized that the existing automatic evaluation metrics for video generation, like FVD and FID, don't always do a good job of reflecting what humans consider to be good quality video.
Right, the metrics don't always capture the nuances that humans are sensitive to.
Exactly. So they wanted to create a more comprehensive and human-aligned benchmark, and that's how OneBench was born. Figure 13 gives you a good overview of the different dimensions they considered.
Okay, let me go look. Wow, it's quite expensive. They cover things like generating large and complex motions, avoiding those weird artifacts that AI sometimes generates, making sure the scenes are physically plausible, ensuring objects stay consistent across frames, and of course, evaluating the overall image quality, including things like stylization. And crucially, they also evaluate how well the model follows the instructions in the prompt, looking at things like object positions, camera movements, and the actions depicted. It's a very thorough evaluation.
Yeah, they really wanted to cover all the bases. And Figure 14 shows how they distributed the evaluation prompts across these different dimensions.
Okay, so how do they actually measure performance across all these different aspects?
They used a variety of techniques depending on the dimension being evaluated. For example, they trained a YOLO V3 model to automatically detect FUM and AI-generated artifacts in the videos. And to assess things like physical plausibility and smooth motion, they used a large multimodal model called QN2DL.
So they're using AI to evaluate AI.
Yeah, in a way. Quen2VL can reason about the content of the video and check for things that don't make sense physically or movements that look unnatural. They also used features from a Dino model to compare frames and make sure objects stay consistent throughout the video. And to check how well the model follows instructions, they used QQuent2-VL again to analyze the video and see if it accurately depicts the objects, their quantities, their arrangement, and the actions specified in the prompt.
And how did they ensure that one bench was actually aligned with human preferences, that it wasn't just based on arbitrary metrics?
That was a crucial part of their methodology. They conducted expensive human evaluations where people compared videos generated by different models, including different versions of one and some of its competitors. They collected over 5,000 of these human judgments, and by analyzing those pairwise comparisons, they figured out which aspects of video quality and instruction following people cared about the most.
Okay.
They then used that information to create a weighting scheme for the different dimensions in OneBench, giving more importance to the things that humans found most relevant. So the final OneBench score is a weighted average of all the different evaluation dimensions reflecting human preferences.
And what were the results of this comprehensive evaluation? Table 2 shows the detailed comparison, right?
Yeah. Table 2 shows how one stacked up against other leading video generation models, both commercial and open source. The results are very clear. One's 14 billion parameter model achieved state-of-the-art performance across many of the key dimensions, often outperforming even established commercial models like Sora, Kling, and Runway. And even the smaller 1.3 billion parameter version of One performed really well, especially considering its efficiency.
That's impressive.
And Figure 15 provides some visual examples that really showcase Wan's capabilities. You can see how well it handles complex motions and transitions, how cinematic the videos look, and how accurately it can generate text within the videos, both in Chinese and English.
Okay, I'm definitely going to check those out. And they also did pairwise comparisons with human evaluators, right?
Yeah, that's in Table 3. And Table 4 shows overall quality and semantic scores, which also highlight Wan's superior performance compared to the other models they tested.
So it seems like Wan has really raised the bar for open source video generation, especially in terms of the overall quality of the videos and how well it understands and follows the user's instructions.
Based on their very thorough and human-aligned evaluation, that's definitely a fair conclusion.
Now, Section 5 of the paper gives us a glimpse into some of the other things Wan can do, beyond just generating videos from text prompts.
Right. That's a really important part of the paper because it shows how versatile and adaptable their underlying technology is. They explored a bunch of different applications, like generating videos from images, video editing, image generation, personalized video generation, controlling camera movement in the generated videos, real-time video generation, and even some early work on generating audio from video.
Wow, that's a lot of different things.
Yeah, and they talk about how the core innovations in Wan make all these applications possible. For example, for the image to video generation, they use a special masking mechanism to control which parts of the video are generated based on the input image. And for video editing, they have this unified framework that can handle a whole bunch of different editing tasks within the same model. And for real-time video generation, they mention using techniques like streamer and consistency models. Figures 18, 21, and 25 in the paper show you from examples of their work on image to video generation, video editing, and image generation.
It's really amazing how they've been able to take this model, which was primarily designed for text-to-video generation, and extend it to so many other areas of multimedia.
Yeah, it really shows how powerful and flexible their approach is.
Finally, Section 6 of the paper discusses the limitations of their work and outlines some potential directions for future research. What are some of the key challenges they highlight, and what are their aspirations for the future of this technology?
Well, they're very honest about the limitations. One of the biggest challenges is still preserving those fine-grained details, especially when there's a lot of motion in the scene. That's something that all video generation models struggle with right now. They also acknowledge that the 14 billion parameter model is still very computationally demanding, which can lead to slower inference times if you don't have specialized hardware or optimizations.
Right.
And they also point out that while WAN is great for general purpose video generation, if you want to use it for very specific tasks, you might still need to fine-tune it on specialized data or incorporate additional domain knowledge.
Okay, so what are their plans for future work?
Well, they plan to keep working on improving the fidelity of the videos, especially for those high motion scenarios.
That makes sense.
They also want to make the models more efficient and scalable so they can run on less powerful hardware and be more accessible to everyone. And they're really big on open source development, encouraging the community to build on their work and create specialized versions of one for different applications.
Yeah, that's really important for driving innovation and making this technology more widely available.
Absolutely. They also want to improve the audio generation capabilities, including adding speech synthesis, and explore new quantization and attention mechanisms to make the model more compatible with different types of hardware. Their conclusion emphasizes that WAN is a truly groundbreaking model for video generation and that its open source nature has the potential to revolutionize the field, leading to even faster progress and innovation.
So as we wrap up this deep dive, let's recap what we've learned about WAN and its key innovations. We talked about the spatiotemporal VAE, which efficiently encodes video while preserving the flow of time. We delved into the video diffusion transformer architecture and its intricate training strategies, including flow matching and sophisticated parallelization techniques. We explored the various ways they optimized inference to make video generation faster and more practical. We learned about their prompt alignment strategy, which ensures that the generated videos actually match what the user intended. And finally, we discussed their comprehensive and human-aligned evaluation framework, OneBench, which demonstrates just how powerful and versatile this model is.
Yeah, that's a great summary. And I think the key takeaway here is that WAN is more than just another impressive AI model. It represents a significant step forward for the entire field of video generation, and its commitment to open source principles is a game changer. By sharing their code and models with the world, Alibaba is empowering researchers, creators, and developers to build on their work and push the boundaries of what's possible with video generation.
It really makes you wonder what the future holds for creative tools, doesn't it? With open foundation models like One becoming more and more powerful and accessible, Who knows what amazing things people will be able to create. It's an exciting time to be following this field, and we encourage all of you listening to check out the linked GitHub repository where you can find the code and models for Wang. We hope this deep dive has given you a better understanding of the technical innovations behind this incredible model.
We aim to provide a more academic and in-depth perspective to satisfy your curiosity about the cutting-edge advancements in AI.
So keep exploring and stay curious. We'll see you in the next deep dive.